So good afternoon, everyone. I'm Pierre Moulinier with the Medical Plastics Division webinar team. And we're very excited together with SPE to bring you a day and a half of technical content pertaining to plastics medical manufacturing. This is our first virtual event. We're very pleased that we're able to operate this way. And certainly medical manufacturing has gotten heightened importance in the last few months.
So what is the cause and effect, all the way from the cleaning procedure to the effect on the end product? So to prevent the spread of HAIs, hospitals, as I mentioned, have increased their practice of wiping medical equipment and any type of high-touch surfaces with both aggressive disinfectants and through increased frequency. So as we highlighted earlier, in the device enclosure housing may be wiped down several times over a course of a day, every hour. And as you accumulate over time, there's a significant exposure to chemicals. So we have a dilemma. While we want to keep the equipment clean, the repeat cleaning often leads to the unintended consequences. So you'll see things such as discoloration, crazing, which is basically the formation of microcracks, and also stress cracking. So once the stress and cracks are initiated in the plastics, the additional use of disinfectants will accelerate and worsen part performance. So the part will be prone to further stress cracking, and then you see a downward spiral in terms of material durability.
Let's talk now about the morphology of the material. And, but morphology as we think of the building block of the material itself. And this is important to understand because this is going to help us get the most out of design and manufacturing with LCP. When we think of a traditional amorphous polymer like a PC or an ABS or a PC-ABS, we have the entangled polymers in the solid state and in the melt state. Semi-crystalline polymer, we have the regions, the crystalline regions. The material becomes more amorphous as it melts for processing. But with LCP, we have this rod-like orientation, and that's what we call a pneumatic structure. So pneumatic structure meaning highly oriented in one direction, and the rods can go over different layers, and we'll show a picture of what that would look like. But that pneumatic structure is what is that high crystallinity in both the melt and the solid stage is what gives us the ability to cycle very quickly and have the mechanicals that we do.
So to lower the incidence of HAIs, you found that these newer, stronger chemical disinfectants were being used a lot more frequently to kill antibiotic-resistant strains and also different kinds of viruses. But that brought unintended consequences because the market started seeing cracking and breaking parts, non-temperature related deformations, some plastic stickiness if they were being wiped down and it was acting as a solvent, and all kinds of different aesthetic concerns, which hadn't really happened in the past. So the result was that there was performance concerns, reliability issues, of course, who was gonna pay for that repair or the loss of the equipment use. If you were a subcontractor to a healthcare facility, saying you were you were a lab or you were some sort of mobile care unit for breast cancer screenings or what have you, you may miss obligations if you didn't have that particular piece of equipment on hand. And then of course, if your part is continually breaking and cracking within the healthcare professionals, you may lose a little bit of brand reputation at the OEM level. And these pictures aren't representative of anybody's individual product, they're just generic pictures. But really the problem cut across all areas. It wasn't just infusion pumps, it wasn't just monitors or supply carts. It was across really the gamut of durable healthcare products, because all of them fall underneath an infection control protocol.
The total duration of exposure in the case of wiping is much shorter, right? You have 10 wipe cycles, a few minutes on average to dry with each wipe cycle, versus 24 hours of continuous exposure in the soap case. And the key, I think, is that what appears to be a dried sample is not really dry. And as water evaporates from disinfectants, the chemistry on the surface changes. And I will come back to that. But first, I wanted to sort the data in terms of products from best to worst, which also leads to some interesting insights. So the PC-ABS blends are the poorest performers here, and PC polyester grades represent an improvement in chemical resistance. The 4 highest performers were 2 PC PBT grades, a PCPET grade, and a flame retardant impact modified polycarbonate grade. And it's generally believed that PC polyester blends are an improvement over polycarbonates for chemical resistance, but this last product of the best performer of all shows that this isn't always the case. Another interesting finding on this chart illustrated is, again, looking at orange with continuous and soak exposure and blue for the repeat wiping exposure, is that there's a bigger difference between the best performers and worst performers in the continuous exposure test than there is in the repeat wiping test. So in that sense, wiping seems to be something of an equalizer, and the ranking is basically the same from best to worst, or very similar, but the soak test may overstate, let's say, the difference between real world performance of materials.
Is the diamond layering process expensive?
The DLC coating layering is a specific coating that is a little more cost effective. However, if you look at the longevity that the parts will remain within your tooling longer, we have numerous components that were once installed into the mold that were standard steel, and customers were constantly having to maintain them over years and replace parts. Once we DLC coated, for instance, like a 2-stage ejection unit, they saw a 3-to-1 increase in the longevity of the part. So yes, it is expensive. However, it pays for itself in the long run.
Obviously, there were some key enablers, and to point out a few close ones, like advancement in ultra-high melt flow material for thin wall molding, 35 melt, 45 melt, and in fact, there's even 55 melt polypropylene, and I know you know which one I'm referring to. Availability of lubricious material compounding with coefficient manipulators such as silicone, EPDM, PTFEs to enhance sliding during molding and demolding, and also reduce or force to fire on the actual instruments. There were also incremental progress made in 3D printable material development with integration of other technology markets such as the Alibaba and also Amazon and many more. One of my all-time favorite is the introduction of the e-commerce outlet by the original material OEMs. Solvay had one of that for 3D printable materials, as you can request for processing data sheets and COA if required. There was also unprecedented progress made around color additives and offerings, as no color was off limit or difficult to compound. Even though colors such as the electric green, the cappuccino reds, and also the sunny happy neons are not preferred, as it may not have vendor approval on file. It may require extensive validation to prove biocompatibility.
So in a sense, we are bringing the flexibility, the low lead times, the low startup costs from 3D printing into the injection molding industry, while keeping at the same time the design freedom from 3D printing very much alive. And this is a value proposition that appeals a lot to injection molders that will today have to buy 3D printers, but will tomorrow be able to use their injection molding equipment for prototyping. The platform we're providing comprises the printers and post-processing equipment itself, as well as the printer materials, the services that are required to keep the printers and the other stuff running. And then we very much want to leverage the installed base of injection mold machines that are already out there. We're really trying to avoid developing or introducing a new paradigm that tries to replace injection molding. We really want to serve as a complement. And that means we will usually collaborate with injection molders that already have injection mold machines on the floor, and we will try to provide them with a more flexible, agile tooling platform.
So we checked for leak on each one of them. The leak test setup and protocol are listed here. There's a picture on the left that shows a press. So we held the part between two compliant materials so it couldn't leak out the ends. So the top material had a hole in it, and that block above it also has a hole, and then you can see that green line coming out to the leak tester. So air pressure goes in through that green line, through the hole into the part, and then there's a solid compliant material on the bottom, which is black, which makes it not leak out the other side. So it's a Centennial leak tester, and what we did is we held the part at 0.75 psi for 10 seconds, stabilized for another 5 seconds, and then we measured the leak over 5 seconds and reported that delta P. The reason we chose 0.75 psi is because that's about the maximum pressure that you see for a hospital ventilator. So that would be the maximum leak rate. Here are the results from that test. There are two axes on there, you can see, two y-axes. One is the delta P, so that's the data that we got directly from the measurement. And then one is estimated loss in milliliters per minute. So that's a unit that you're going to more typically see in ventilator literature. And the estimated loss was calculated by taking the delta P, using the volume and the temperature and the pressure of the part, and figuring out how many moles were lost. So there was a molar lost, and then that was converted to STP, and so we could get a milliliters per minute at STP loss, which is exactly what the ventilator we could compare to the leak rate that's within the threshold. So the control part had no leak. That's not a surprise. It's made for exactly this purpose, so it's a good thing it doesn't leak. The SLA also had no leak, so that was good to see that it's a very non-porous material, the way that it prints upside down, layer by layer with the UV cure. You get basically no pores. The FDM definitely has some pores. We did see a minimal leak with the PLA, and then the ABS material exceeded the limit for our measurement technique. So from 0.75 psi, it leaked down below 0.25 psi within 5 seconds. So I have an arrow pointing up from the top of that bar because we know it exceeded our test, but we don't know by how much.
In this design, so you can see there's a N95 insert within that printed assembly there. 5 to 6 filter inserts could be made out of one N95 mask to make those masks last longer. Some feedback from first responders. They were in dire need of masks, and in some instances were just using what they could in certain instances. But when responding to calls, the first responders were required to wear goggles and N95 masks. And the SCBA, or self-contained breathing apparatus, could be utilized and provide a safer and better solution while extending the mask life. When we look at the timeline for accelerated development and launch of this product, the idea and the team was formed on March 20th. So this leads into the human-centered design innovation process at Extol. We utilize Scrum as a framework for rapid prototyping, rapid product development, as well as getting feedback from our customers. So a Scrum team was formed on the 20th. And then on the 27th, so the next Friday, we had a fully operational, the version was Scott AV3000, was the first SCBA version that we developed, and it worked. And we went live with the product on our website on the 27th. On the 28th, we received our first orders. And then within those next few days, we were 3D printing test fixtures that you can see here to test the leak and the seal to the mask itself, and then orders shipped. So we went from idea to shipment within 13 days in this instance. Over the next several weeks, we had multiple requests for different versions. So we had 5 more versions that we developed, different versions of the SCBA mask. We had firefighting departments send in masks that we could reverse engineer adapters for, as well as we utilize CT scanning on one to get a better, quicker fit up and accelerate development even further. And to date, 500 plus of these adapters have been produced.
So I just want to highlight here some of the applications that are taking place using photopolymers. One that I'm really excited about are tooling and mold inserts. Because we now have resins that when printed have a high heat stability, there's actually folks that are using this technology to make the tool, make the mold. And if you have, say, a very short run or limited run production, you can print a tool. You may not get 1 million shots off the mold, but you may get 1,500 and enough to make enough parts for your limited application. Also, midsoles for shoes. I'm showing here just examples from a company, Henkel, who's printed these midsoles using their materials. And then also silicone medical models. You see like different shaped hearts and hands that you can print as models. The automotive industry is heavily involved in additive. Companies like BMW, Mini, and Rolls-Royce are all partnered with carbon to make different automotive parts. And then a company out of Boston, BMF, is focused on much smaller scale parts with really high resolution, things like microfluidic chips and applications in electronics. And so we're excited to see what the new applications might be and what might be coming next.
So let's go over some examples. Here is an example from the KSA itself, the Saudi Arabia colleagues. In response to the rapid spread of corona, the Ministry of Health of Saudi Arabia called upon local manufacturers to produce FDA-approved ventilators. And our application development experts helped the local OEMs to reproduce Medtronic's COVIDian ventilators under the company's given permissive license, which was specifically given for the purpose of addressing the coronavirus situation. Also, example on the right, 3D printing of large numbers of ventilator splitters, manifolds for hospital use in the region. We provided the material positioning to the OEMs for the ventilator and supported the redesign with predictive engineering, correlation studies, supplied tooling and processing know-how, and supported final application testing and validation.
Okay, then I'll move on to why meltblown is the material of choice. Okay, so as we have pointed to you in the previous slide about the physics of this filtration, there needs to be successive layers of fabrics to really capture out the large particles. But also there needs to be high surface area. There needs to be very small of these gaps or holes through which the particles can flow through. And there should be some mechanism to also capture the superfine ones by these high surface area substrates. And to make these in a rapid fashion and in a large scale, very few technologies are able to offer that. For example, even if you weave and you make all these garments from poplin or plain weave fabrics, twill weave fabrics, so shown in the right-hand pane here, they still have gaping holes through which these virus can pass through. And so these are not really effective in filtering out the particles. They are effective in stopping the particles from going out of the wearer's efflux, right? So that's really, so it's still useful to wear those, but it's not really effective for the wearer. And you can't be sure that, okay, now that I have a bandana, I can go do everything.
Great, thanks.
You're welcome.
We have a question that's come in from Don DeMello of Celanese. Do you work with other hard to print polymers like PE, besides PE like POM, acetal? So again, I think that kind of stems off your initial question, but go ahead.
Yeah, so again, the short answer is no. When you look at the olefin family, there's a lot of different materials out there and a lot of different blends, but it does need to have that olefin content. For example, when we get into like polypropylene, you might have a 20% talc fill because you're putting it in a high heat environment, or maybe you have 20% glass fill because you're trying to get some rigidity out of it. When we start to go into the soft touch materials, like EPDM plus PP, to get different durometers there, you have different content levels of the EPDM rubber versus the polypropylene material with it. And so there needs to be enough of a olefinic content in order for our system to work. But again, that's been our focus and continues to be at this time.
I want to credit my colleagues, Pierre and Victoria, for their eagerness and openness to pursuing this. We, as Pierre coined it, it was kind of a science experiment. We'd never done it before, so we didn't know what we didn't know, and we were willing to try it. And just want to applaud them for their great effort and leadership on putting this together. I want to say thanks to Neil and AJ, our colleagues from the board of medical plastics, for their contributions and helping with acting as moderators. A lot of great talks that we heard over the last day and a half, and want to certainly make note of that and thank our great speakers and their contributions. And again, their openness to trying this concept, and specifically thank our sponsors for helping make this a reality. Some great presentations from our sponsors as well. Thanks to headquarters for all the support. I'll open it up to Pierre or Victoria, or I think Anil's on the line. If you guys have any closing comments or remarks.
Nothing to add, Ned. You captured it all. Thank you. Thank you to everyone. I think, yeah, I'm very pleased with the last day and a half. I hope that everyone else that listened in, and I hope that anybody that helped with the organization felt it was worthwhile. If there's things that we could do better, we're certainly open to hearing about it, and you know how to reach us, and just let us know.
And this is Victoria Nawabi. I would like to thank our presenters and our participants. As Ned and Pierre have mentioned, this was the first time we were putting a virtual conference together as such. And so there are some lessons that we have learned, and we're hoping that our next event that we will organize would be even more successful than this one. I have already received some very good comments from the participants and even some of the presenters, and I would like to ask everyone, feel free to send us an email if you would like to share your opinion. It would be a way for us to receive feedback so that we can implement it in our next meeting. And really, this meeting was a goal for us to highlight how our professional community has come together to support the medical community in a very short time frame. And thanks to SPE for allowing us to do this.
And thanks to all of our attendees for making the event possible. So